So welcome to the 12th and last week of the parameterized algorithm course in 2024. So this is 14th October and there will be one more session, an extra session, most likely this Saturday on 19th October. I'll let you know. So in this week, we will discuss uh, some assignment questions from last year's offering, and this will help us solve the assignment this year, hopefully. So before we get started with the questions, let us recapitulate two definitions. One is of vertex cover and the other is of dominating set. So in the vertex cover question, we are given as input a graph G and an integer K. And the question that we are interested in is the following: that can you find, okay, so G, let us say, has vertex set V and edge set E. So I'll write G as V comma E. So the question is, does there exist a subset S of the vertices, okay, such that for every edge U comma V in the graph, so one of U comma V is in S. So S intersection U comma V is non-empty, and the size of the set S that you have picked is at most K. All right. So you're interested in picking a subset S of size at most K of the vertices, such that every edge is covered. That means for every edge, at least one of the endpoints is in the set S. Okay. So there's a similar question, that of dominating set, and here the input is same. A graph G equals V comma E and an integer K, and the question is similar. The question is, does there exist a set D of the vertices, okay, such that for every vertex V in the graph, either V is in D or V is adjacent to some vertex in D, and the size of the set that you have picked is at most K. Okay. So this is the dominating set question. So are these two questions the same? So are these two questions same? That is the first thing we should ask ourselves. Or are these two things different? So let us take an example. So let us say this is our graph, and let us say these vertices are named A, B, and C. And let us say that K equals to 1. So does there exist a vertex cover of size less than equal to 1. So of course, vertex cover of size 0 cannot exist. So the question is, does there exist a vertex cover in this graph of size 1? So you have the liberty to pick any of the vertices. So let us say I pick vertex A. So with vertex A, how many edges can I cover? All the edges that are incident to A. So two edges are incident to A, AB and AC. These two can be covered. All right. But BC is not covered. So therefore, picking A is not sufficient to cover all the edges. So A alone cannot be a vertex cover. Similarly, the same argument will go through for picking B alone or picking C alone. So therefore, a vertex cover of size 1 in this graph is not possible. Oh, I need to charge my pencil. So I think it is clear that why a vertex cover of size 1 won't be possible in this case. So similarly, we can ask that in this graph, does there exist a dominating set of size at most k? So of course, a zero size dominating set is not possible, does not make sense. So the question is, does there exist a dominating set in G of size 1? So I'll give you a minute to think about it. All right. So I hope you had a chance to think about it. So let us see if we can find a dominating set of size 1 in this graph. So let us say again we pick this vertex A. And if we pick this vertex uh, A itself is dominated, and B, because of being adjacent to A, is also dominated, and C, because of being adjacent to A, is also dominated. So by definition of dominating set, so every vertex is either in D. So in our case, D is the single vertex set A. So either so every vertex is either in D or is adjacent to some vertex in D. That is true in this case for each of the vertices, and therefore taking A alone constitutes or forms a dominating set. So we can conclude that yes, A is a dominating set. All right. So these two concepts are different. Vertex cover and dominating set are different. So now we can ask, uh, or rather, we can look at the relevant assignment questions. All right. So I think I have the assignment questions here. Yes. So I think this is visible. Okay, so it cannot be made any larger. Mhm. All right, so I'll let you read the questions. So first is, what is a split graph? So a split graph is a graph G whose vertex set can be partitioned into two sets, such that the subgraph induced by one subset is a clique C, and the subgraph induced by the other subset is an independent set I. All right. Now the question is pertaining to split graphs. So which of the following statements are true about split graphs? So first we look at the first statement, that is vertex cover is NP hard on split graphs. The second statement is related, that vertex cover is polynomial time solvable on split graphs. So one of these things will be true. Either it is NP hard to find the vertex cover on split graphs, or it is polynomial time solvable to find the vertex cover on split graphs. So I think the definition of split graph is clear. So pictorially, so the vertex set can be divided into two parts. So one part is a clique and the other part is an independent set. So that doesn't mean that there are no edges between the two parts. So between the two parts there could be edges, but one part induces a clique and the other part induces an independent set. Okay, so now I'll give you a few minutes to think about whether finding the vertex cover is going to be NP hard on split graphs. So we have seen the reductions from known NP hard problems in this week. So if the vertex cover problem on split graphs is NP hard, then one should find a reduction from a known NP hard problem to this problem. Otherwise, one should design an algorithm that runs in polynomial time and finds a vertex cover for split graphs. All right, so I hope that you had a chance to think about it. So finding the right problem from which to do the reduction is itself a challenging question. But if you have not been able to find the right problem from where to reduce, let me warn you that there is already a polynomial time algorithm for vertex cover on split graphs. So let us look at this algorithm. So, so you know that you are given a split graphs. So you know that which part is the clique and which part is independent set. So you know the partitioning of the vertex set such that one part is the clique and the other part is the independent set. So concentrate on the part which is the clique. So let us say There's a set of vertices that form the clique. So you are willing to cover each of the edges in the clique. So let us say that the clique size be, I don't know, maybe small c. So let us say the clique size is small c. So the c vertices that participate in the formation of the clique are there are c vertices in the partition corresponding to the clique. So there are, so mod v, so that means the size of the independent set is, so mod v, that's total number of vertices minus small c. All right. So first question is to cover the edges in the clique, how many vertices are required? So if you take all the vertices of the clique, then definitely all the edges will be covered. So definitely the vertices will suffice. If you take all the vertices of the clique, then definitely all the edges in the clique gets uh, covered. But if you take one less, so consider a clique. Let's say for demonstration we have a 4 clique. So if you take 3 vertices, okay, then do all the edges get covered? So there is a 4 clique and you want to cover the edges of this clique, then will 3 vertices suffice to cover the edges? So the vertex that you have not taken, whatever edges are incident to that vertex is definitely incident to another vertex, and therefore all the edges are also covered because you have taken all the remaining vertices. So 3 vertices will be sufficient to cover all the edges in the clique. So in this case, c minus 1 vertices will also be sufficient. But how many edges are required on the independent set sides? So this side on this, so the remaining vertices, which among themselves form an independent set. So therefore, there are no edges among the vertices of this independent set. So in this partition, these kind of edges are not there. But there could be edges from one side to the other side. All right. So there could be edges like this. There could be an edge like this going across the two partitions. So now you have to ask that, okay, how many vertices I have to pick additionally to cover such kind of crossing edges? Okay, so which goes from the clique side to the independent set sides. So of course, if you take all the vertices in the clique side, then all these crossing edges are also covered because the crossing edges definitely have one endpoint in the clique side. Okay, so but if you take only c minus 1 vertices from the clique side, then what will happen? So it may happen that one vertex in the clique side that you have not picked, that is an endpoint of one of the crossing edges. In that case, such crossing edges for which uh, this vertex on the clique side is an endpoint, such crossing edges remain uncovered. So, but to check whether that is the case, we do not need much time. In fact, we do not need more than mod v time, because on each side there are mod v, at most mod v vertices. Okay. So, but how many candidate C minus one size vertex covers you have? So, how many candidates do you have to check? So, remember that there are C vertices in total in the clique side. So, in how many ways you can pick C minus one of these vertices? That is the question. So, of course, you have the liberty to leave out one of the vertices in the clique side, and there are total C vertices on the clique side. So, therefore, you can form a C minus one subset in C ways. So, there are C candidates. So, there are C vertices in the clique side, and you want to pick C minus one of them. So, you have the liberty to leave out one vertex. So, which vertex to leave? There are C options. So, therefore, total there are C candidates. So, the number of candidates. Why is the pencil not working? Just give me a minute. So there are C candidates. So for each of these candidates, you can verify in at most order v time that whether this is forming a vertex cover or not. So for each candidate, you may require polynomial time is required. To check if it is a valid vertex cover. All right. So one may ask that why are you not bothered about picking vertices from this side? Because this could also be possible to take vertices from this side. So you know that because on this side there is a clique, you must require at least C minus one vertices to be taken from this side. Now after that, one vertex could be left on this side. Now, if this vertex is connected to another vertex on this side, then you have to take at least one vertex to cover this edge. But if this vertex is connected to multiple edges, or rather this vertex is in, multiple edges are incident on this vertex, then taking this vertex alone can cover all these crossing edges. So therefore, we can focus only on this side, because if you have to cover crossing edges, multiple crossing edges that are incident to one side, and you are taking more vertices from this right side, then you are not doing it optimally. So therefore, we only concentrate on this side, and we can check whether C-1 vertices are sufficient to cover all the edges in this graph in polynomial time. So therefore, this entire scheme together is a polynomial time algorithm to find a vertex cover in a polynomial time, rather the minimum vertex cover in polynomial time on split graphs. So therefore, since we have shown the existence of an algorithm, therefore this statement that vertex cover is polynomial time on split graphs is true, whereas vertex cover is NP hard on split graphs is false. Okay. Fine. So I think this is understood. If you have any doubts, you can ask me. Okay, so let's focus on the next statement. So dominating set is known to be fixed parameter tractable on split graphs. Okay. So whether this statement is true or false. Let me go to the next page. So let me copy this diagram once again. So very interested in the third statement. So if dominating set is FPT on split graphs, so let us say first we have to specify the parameter, the fixed parameter tractable with respect to which parameter. So let us say the parameter is the solution size, that is size of the dominating set. Okay. So let us say, so as usual, the graph is given and the parameter k is given. So if you can find an f of k times n to the constant running time algorithm, then we will say that this problem dominating set is known to be FPT on split graphs. So what do you think, whether this is FPT, whether we can find an algorithm with this kind of running time to find the dominating set on split graphs? You can also look at the next statement. So one of these statements is true. Either dominating set is FPT on split graphs, or it is unlikely to admit an FPT on split graphs. So if you want to say that this is false and this is true, then you should show some reduction from a known problem for which an FPT algorithm is not likely to the dominating set problem on split graphs. Okay. So for example, if you look at the problem of dominating set on arbitrary graphs, it is known that uh, this problem is unlikely to admit an FPT algorithm on split graphs. So looking at dominating set on arbitrary graphs, so it is unlikely that there is an FPT algorithm for this problem. So this is also known to be a W2 heart problem. Okay, so if somehow we can manage to show a parameterized reduction from this problem to this problem of dominating set on split graphs, then we will prove this fourth statement, that it is unlikely to admit an FPT algorithm on split graphs. So we have to decide about these two statements. So next statement is also related. It says that there exists a parameterized reduction from dominating set on general graphs, which I said arbitrary graphs, to dominating set on split graphs. So if this is true, then this is also true, then this is false. So let us look at whether there exists such a reduction or not. So here is the next statement, which shows or which proposes such a reduction. So let you read this statement, whether this statement is true or not. Okay, I think the connection is stable. So here is the reduction. So given a graph G, consider a graph H where the vertices of H are two copies of the vertices of G. So first you make two copies of the vertices. So this is let us say copy 1, and this is copy 2. Okay. So you're constructing H from G. So G is an arbitrary graph, or rather a general graph. So first you make two copies of the vertices of G. The edges of G are such that, so it should be edges of H. I think it should be edges of H. So now we have to define what are the edges in this in this graph H. So the edges of H are such that all the pairs of vertices in the first copy of G have an edge between them. So you construct a clique on the left side, that is, you construct a clique among the vertices in the first copy. So you made two copies. In the first copy, you construct a clique. Okay, I don't know. I may not have drawn all the edges, but yeah. So let us believe. So you have to draw all the edges so that on the left side you have a clique. And what are the other edges? For all vertices in the original graph G, there are edges from the copy of U, from the first copy to the copy of all vertices in the closed neighborhood of U. So what is the closed neighborhood of U? So the closed neighborhood of U is a set of all vertices incident on U and includes U. So in the set you will include its neighbors and U itself. Okay. So now you draw an edge from U to a copy on this side. First of all, to U to so if this is U, then this other side there's a copy of U. This edge you add, and all other edges you add depending on whether this edge existed in the original graph. So if this is V and this is U, and U and V were neighbors in the original graph, then you will add an edge between this side U and that side V. All right. Okay. So the graph H is a split graph. Yeah. So yeah, that's all. So that is a description of H, and this claim is that the graph H is a split graph, and G comma K is a yes instance of dominating set, if and only if H comma K is a yes instance of the dominating set on split graph. So there is a reduction. So first we have to verify whether this is indeed a split graph. So first such edges are there. So this to this there is an edge. So from every vertex to itself, I mean two copies of the same vertex will get an edge. And this could be, there could be other edges. Other kinds of edges could be there. I don't know, depending on what are the edges in the original graph. All right. So now is this split graph? That's the first question. So what is a split graph? So a split graph is a graph whose vertex set can be partitioned into two parts. One part is an independent set and the other part is a clique. So clearly one part is a clique, that is as per the construction, whether the other part, the induced graph by the other part, is an independent set. It is an independent set because among the vertices in the second part, that means these vertices which the second copy of the vertices of G, among them there are no edges. So the edges are of nature crossing, only crossing edges. And of course, on the first copy, there is a clique. So in the second copy, there are no edges among the vertices of the second copy. So therefore, this copy, second copy, forms an independent set, and the first copy is a clique. So therefore, this is definitely a split graph. So now we have to verify whether G comma K is a yes instance of dominating set if and only if H comma K is an yes instance of dominating set. So you have to verify this thing. Now I'll give you 1 minute to think about it. So let us say, so there are two parts to the proof. The first part is, suppose that G comma K is an AS instance of dominating set, then this graph that you have constructed H comma K is also going to be an AS instance of dominating set on split graph. First of all, this is split graph we have seen. The other side is, assume that H comma K is an AS instance, then a G comma K is also going to be an AS instance. Okay. So first, let's say the first part that G comma K G comma K is a yes instance. So what does this mean? So that means there is some subset of G, let us say S, of size at most K, which is a dominating set. So there exists a dominating set in G of size at most K. So from this dominating set in G, can I construct a dominating set in H? That is the question we have to ask. So what we can do is, we look at the vertices of S and look at the corresponding vertices in H. But then in H, there are two copies of each vertex. Okay. So let us concentrate only on the first copy. So let us say that this let's take orange color. Yes, orange is there. So let us say this vertex, this vertex, this vertex, this vertex, this vertex, they form. Of course, if you take all the vertices, they will form dominating set. So in the graph G, you have been given a dominating set of size K. Let us say K, exactly K, and that is S. And if you look at uh, the corresponding copies of the vertices in S, in the clique side, then these copies taken together is going to form a dominating set in H. That is the claim. Let us take a concrete example. So let us take our easiest example with which we started. So let us say the graph G is a triangle. So H will be like this. Okay. No, say, I mean, yeah, we are interested in dominating set. Fine. So now we have to draw the edges. So A1 will get connected to, okay, this will become a full tree. Sorry, this will become a complete graph. So let's say one more edge is there. T is also there. This is T1. This is D2. So A1 to A2, there is an edge. That is as per the, what to say, description of the construction of H. So all the closed neighbor. So in the closed neighborhood of A, which all vertices do you have? So A has neighbors B and C. So A1 will get connected to itself and to B2 and C2. Okay. Now how about B1? So B1 will connect it to itself. I mean its own copy. And B was neighbors to A and C. So B1 will get connected to A2 and C2. Okay. C1 will get connected to C2, and C was neighbors to all of A, B, and D. So it gets connected to all of these other vertices in the second copy. All right. So now here is a dominating set. Here, which is a dominating set. If you take C itself, C is a dominating set because all other vertices are adjacent to C other than C. So now my claim is that if I take the first copy of C alone, that is a dominating set in this graph H. So that is true because C1 by virtue of being part of a clique. Oh, so these other vertices have to be connected. So they are forming a clique. So that is by construction. All right. So that is by construction. So by construction, there are no, so these kind of edges are not there. So let's look at the construction of H once again. So you make two copies of the vertices of G. On the one side, the first copies together, they form a clique. So that's why we have a clique here. And the right side, the second copies themselves are independent, but we will draw crossing edges depending on the edges in G. So in G, there are four edges. So these four edges have led to these kind of crossing edges. So now C1, by virtue of being part of this clique, is able to cover all the vertices in the first copy of H. Now in the second copy vertices, if you look at it, so C1 is connected to itself. So this edge is taken care of, is covered by it, or rather not edges. I mean, this is C1 since by definition is connected to C2. So C2 is dominated by C1. And because C is able to dominate the other vertices in the original graph, so C will also be able to dominate the other vertices in H, the second copies. The first copies are definitely dominated by virtue of being part of the clique. So that is how dominating set S in G will give rise to a dominating set S dash. There exists a dominating set S dash in H of size at most K. Okay, so you just take exactly the same vertices that are in S, but only the first copies. Okay, you don't have to take all the sort of first copies, only those first copies which are in S. That will be sufficient. Okay. So one side we have verified that if GK is an ES instance, so therefore HK is also going to be an ES instance. All right. So now we have to see the other part. So I think this part is clear. If it is not clear, then you can ask me. All right. So let's go ahead. So let's look at the other part. Okay. So what is the other part? So the other part will assume that H comma K is a ES instance, and then we will prove that G comma K must be a ES instance by showing a dominating dominating set of such size. Okay. So let us assume. So let's go down. So assume that H comma K is a ES instance. So what does it mean? So this means that there exists a dominating set S in H of size at most K. Now what we have to show? We have to show that there exists a dominating set S dash in G of size at most K. So how are we going to show it? So consider H. So H is sort of like this. This is our H. So let us take it from here. So this is our H. So H looks something like this. So this is how H looks like. So there is some set of vertices that form uh, this dominating set. So let us say some vertices from this side and some vertices from this side, they form a dominating set. So you take all the original vertices. So if this is a copy of some vertex u in the original graph, then you take u. This is a copy of some vertex v in the original graph, then you take v. So you take all the original vertices. So to put it formally, each dominating set T of H will give rise to a dominating set of G, which consists of original vertices in G corresponding to all the vertices in T. So corresponding to, I mean, corresponding to all the vertices in S.
Hello.
Yes.
Siddharth, there is some problem in this voice. I mean, it's not clear.
Okay. It's not clear to you.
Yes, yes,
Okay. So is it muffled?
yes.
So I cannot verify it right now. Uh,
It's very like heavy voice, and I don't know what is the issue. Maybe I'll disconnect from my end and join again. That might work.
yes, yes. I'll wait for you.
Yes. Hello.
Yes.
Oh, it's fine now.
Okay, okay. So
Okay.
I think there was some issue in this other account you had logged in with.
Yes, yes, yes. Maybe yes.
Okay,
Yes,
okay.
it's clear now. Okay.
Okay. So I was talking about this statement. but it is towards the end of the discussion.
Hmm.
Uh, yeah, so I was showing that if there is a yes instance for the constructed graph H, that means if there is a dominating set of size at most k in the constructed graph,
Hmm.
then there is a dominating set of size at most k in the original graph also.
Okay.
Uh, yeah, so if you have looked at the construction of H,
Hmm.
then you can see that corresponding to all the vertices in the dominating set S of H,
Hmm.
if you take the original vertices in G, then by definition these original vertices is going to form a dominating set in the original graph G. So that means this statement is true. So now the other statements we have already seen. So let's look at the other statements. So yeah, we said that, okay, we say that if there is a polynomial time reduction from the dominating set of on general graphs to the dominating set on split graphs, then the dominating set on split graphs is going to be as hard as the dominating set on general graphs. We also said that it is known that the dominating set on arbitrary graphs is W2 hard. So therefore, with this polynomial time reduction, which is also parameterized reduction, we can conclude that the dominating set on split graphs is also W2 hard. So this statement that there exists a parameterized reduction from dominating set on general graphs to dominating set on split graphs is true, and this is the reduction. So both these two statements are true. And they are dominant to admit an FPT algorithm. So this is true. So this is true. A dominating set is unlikely to admit an FPT algorithm on split graphs. And a dominating set is FPT on split graphs is definitely false. Okay. And these two things we have already seen. This is true and this is false. We have seen this algorithm. Okay. So now this is the last statement that we will see. In fact, these two statements are almost same, except that there is a small difference. So I'll first let you spot the difference between these two statements and then we can talk. So the difference is only here. So
Siddharth,
yes.
just can you give a quick review of the problem once again?
Okay, okay, fine. Uh, so we are looking at dominating set.
Hmm.
So this is the definition of dominating set.
Yeah, so definitions are finite.
Oh, okay, okay. So now this whole question is asking
Hmm.
whether the dominating set on split graphs.
What are split graphs?
What is a split graph? So you were following when I was talking about split graph. Am I audible?
Yeah, yes.
So a split graph
Hmm.
is a graph where the vertex set can be partitioned into two parts.
Okay.
Okay. So one part induces a clique and the other part induces an independent set.
Okay.
So here among the blue vertices, there are no edges,
Hmm.
but among the orange vertices, that is the other side,
Hmm.
there is a clique. So they form a clique. Okay. But
Okay.
there could be crossing edges. That
Hmm.
means one endpoint lying on one part, the other endpoint lying on the other part. So if that is the structure of the graph, then we
Hmm.
call it a split graph.
Okay.
So we know that the dominating set on general graphs is W2 hard. So that means
Hmm.
in layman words that no fixed parameter tractable algorithm is expected for dominating set on general graphs.
Hmm.
So that means algorithm that runs in f of k into n to the power constant time is not expected, where k is the size of the dominating set.
And fk is a polynomial in k.
No, fk is any function. It could be 2 to the power k.
Okay. Okay.
Yes. So fk is an arbitrary function.
Hmm.
So such a running time is not expected. That means even if you are allowed to take 2 to the k times n to the
And
constant time, then also you cannot find an exact dominating minimum dominating set for
hmm.
general graphs. Now this whole reduction, this entire sentence is a reduction
Hmm.
that reduces the dominating set on general graphs to the dominating set on split graphs,
Okay. Okay.
and which implies that the dominating set on split graphs is
Split graph
equally
is.
hard.
Hmm.
So the dominant this sentence, I'll just recap once. So what they do is very simple. So they take any graph G. So they make another graph H, which is a split graph. So from G is any graph. From G they construct an H, which is a split graph.
Hmm.
So now they show that if G has a dominating set of size k, then H will also have a dominating set of size k.
So, given any graph, can we like how do they construct this split graph out of it?
Yes. So your voice
The
was so
edges
you're
or
asking how this.
yeah, from G, how do we construct H?
So you make two copies of the vertices of G. So this is
Oh.
one set, and this is
Hmm.
the other set.
Hmm.
So initially there are no edges, only the two copies.
Yes.
Okay.
You make
So
one
now,
set a clique, other independent
yes,
set.
yes, 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 yes.
Okay.
So this they make a click, and the other side there is an independent set.
Hmm.
Now to encapsulate the edge relationships in the original graph, they draw some crossing edges.
Okay.
So for every vertex u in the original graph,
Hmm.
they draw edges to those copies.
Which are neighbors of.
Uh, yes, which are neighbors of u, including u.
Hmm.
So these crossing edges are formed. And now they can show that if G comma K is an AS instance, that is, if in the original graph there is a K sized dominating set,
Hmm.
then they can construct a common K sized dominating set in H also. So how do they do that? So here is an example. So let us say this is G. So first you make two copies. So
Hmm.
A, B, C, D are four vertices. You make four vertices A1, B1, C1, D1, and four vertices A2, B2, C2, D2.
Hmm.
So there is a clique here, and there is an independent set here,
Independent. Yes.
and you have drawn these crossing edges which are shown in
Yes.
brown. So now you see that C alone is a dominating set.
Dominating set. Right.
So in the first copy, you take the corresponding
What?
uh, copy C1.
Hmm.
That is going to be a dominating set because all the
Oh.
vertices of the clique are already dominated by C1,
Hmm.
and the vertices of the independent set, that is the other side, is also dominated by C1 because C itself is a dominating set in the original graph.
So if we have a subset of vertices in G, which is a dominating set, it will be if we select those vertices in the first copy where
Yes,
which induces a clique, that is going to be a dominating set as well for H.
exactly, exactly. Yes. So you get an exactly equal sized dominating set in H
Hmm.
also. Now in the other direction, if
Hmm.
H has a dominating set of size K,
Hmm.
then maybe these vertices are taken from both sides,
Hmm.
which are in the dominating set. Then you take the corresponding original vertices in G,
Hmm.
and because all the other vertices, so
Some may repeat and
yes,
we'll get
yes.
a smaller size dominating set in the.
Yes, yes. All the other vertices already dominated in the
Hmm.
so this crossing edges are simulating the original edges only. So in the
Yes.
yeah. So that is the other direction, that if H has a dominating set of size K, then G will also have a dominating set of size K is also true. So thus we prove that even for special class of graphs called split graphs, dominating set is what is called W2 hard. Okay, so we will take one question now. The second one. Okay, so this is again about reductions. So today's week is about reductions and hardness. This discussion is what to say, centering around reductions. So let's look at the first statement. So there does not exist a parameterized reduction from set cover to dominating set. So that means the hardness of set cover is not equivalent to the hardness of dominating set. The second statement, there exists a parameterized reduction from set cover to dominating set. Okay, and that means that the hardness of set cover and dominating set is equivalent in one direction. The other direction also needs to be proved. So there exists or there does not exist a parameterized reduction from dominating set to set cover. So this is so I think we can recall the definition of set cover first. So here you are given an universe U. Yes, a family of subsets of U and an integer k. Okay, this is the input, and the question is, does there exist a subfamily f prime of f such that union of these subfamilies is the universe, and of course the size of the subfamily is at most k. That is the question. And dominating set is something we have already seen. Now we have to establish or uh, rule out the equivalence of these two problems. Okay. So if there is a, let's try to establish equivalence. So if there is a parameterized reduction from set cover to dominating set, then we should be uh, able to convert an instance. Let's do the other way first. So convert an instance of dominating set into, okay, into an instance of set cover. That is the first task, that you are given an instance of dominating set and then you convert it to an instance of set cover, and then you have to show that an ES instance here is going to lead to an ES instance there and vice versa. Okay, so I would say that is the first job, and the second job is prove that an ES instance of dominating set implies if and only an ES instance of set cover. Okay, so this is 724 now. So I think at this point we can take a break, and I will also encourage you to sort of do this exercise. So it is 7:25 now. We will come back at 7:35 p.m. We're going to resuming at 7:35 p.m. All right. So welcome back again. So I hope that you had a chance to think about this question. So we'll try to give a reduction. So there are two steps to the reduction. So first is to convert. Yeah, I think I'm audible. So the first is to convert an instance of dominating set into an instance of set cover. So what is an instance of a dominating set? It's a graph G along with uh, integer parameter uh, k. So you have G comma k, which is an instance of dominating set. All right. So from here you want to get a set cover instance. Okay. So you have the graph. So what you do is you consider the vertices of the graph and denote for each vertex v in the graph, denote by S sub v as the closed neighborhood of the vertex v. That means all the neighbors of the vertex v along with the vertex v itself. Okay, so these are the sets for your uh, set cover instance. Okay, and the universe for the set cover instance, what should be the universe be? The universe for the set cover instance should simply be the vertex set. Okay, and then the families of the set cover instance are nothing but these SVs, or I'll just say FVs, F sub V. By FV I denote a subset of vertices which are the neighbors of the vertex V along with the vertex V itself. So now this is our set cover instance. U, and let us say the union of these FVs is F. So F is the union over all this uh, so F is the union of all these FVs. So now your set cover instance is U comma F comma K. So K remains the same. So this is the first step of the reduction. That is, you converted the instance of the dominating set into an instance of the set cover. The next step is to prove that if there is a dominating set of size k, then that means there is a dominating set of size set cover of size k in the constructed instance also. Okay. So first, let us suppose that there exists a dominating set of size k, and let us say this dominating set is denoted by D. Okay. Now, so consider the union of those FVs such that V belongs to D. So this is a set of this is a subfamily. So now the claim is that this is nothing but the universe. So the universe itself is this union of these FVs corresponding to those vertices which are in the dominating set. Okay, so how we shall prove it?
This follows by the definition of dominating set itself.
Yes, yes, yes. That is true. Yes, so because D is a dominating set. So every vertex is either in D or is adjacent to D. Now, what is your universe? So your universe is a set of all the vertices. So the neighbors of the dominating set, including the dominating set, is going to be the universe, and therefore it is going to cover all the elements of the universe. So that's and because the parameter is also preserved, so if there are k vertices in the dominating set, there are exactly k sets in the set cover that you are producing. So therefore we have a what is called parameterized reduction from the set cover to the dominating set in the dominating set to the set cover in one direction. The other direction also we have to prove. So the other direction is, if there is a yes instance, so the other direction is the following. uh, so suppose there exists a set cover of size k in the constructed instance. So let us say the set cover is denoted by S. Then we have to prove that this must imply that there exists a dominating set of size k in G. Right. So how shall we prove this? So the sets that form the set cover covers all the elements of the universe. Now the sets in the dominating set setting are corresponding to vertices. Okay. So every set is some vertex and its neighborhood. So if you take the corresponding vertices of the set cover S, then you essentially ensure that all the vertices in the graph are dominated, because every set in the set cover is corresponding to some vertex dominating some other vertices. So now, since the set cover includes all the vertices in the universe, therefore the corresponding vertices dominates all the vertices of the original graph. So the other side is also simple. So all right, so one can do it more formally, but I did it like this only. But you can do it more formally. So we will say that there is a, so this one is true, that there is in fact a parameterized reduction from set cover to dominating set. And there is also, so we haven't seen this, we have seen only this. So from set cover to dominating set means you have to show the first step. The first step is to start with an instance of set cover, and then from this instance you obtain a instance of dominating set, and then show that if there is a yes instance of the set cover, then that implies an yes instance of the same size for the dominating set. So this part is also true, but I will leave that to you to think about it. All right, so you start with the set cover instance and you go to a dominating set instance. Maybe I'll give you an overview of how to go about that. So you start with a set cover instance. So what is a set cover instance? So u comma f comma k. Okay, so F means curly F. Okay, so U is the universe, F is the family, and K is the maximum allowed size of the set cover. So from this, you want to obtain a graph G along with the parameter, which is nothing but the dominating set instance. So how do you go about that? So construct a graph G with a vertex corresponding to each set S in the family. So for each set in the family, construct a vertex. So you have as many vertices in the graph G as there are sets in the set cover instance. So let us say that these are the vertices. So these vertices is corresponding to the sets. Okay. So now you have to define the edge relationship. So if okay, so additionally, okay, so you have only captured the sets. You also have to capture the, so you have captured this part. You also have to capture the universe elements. So let us say, so for every element in the universe, you have vertices. So for every element in the universe, construct a vertex. So now we can define the edges. So if an element E belongs to a set S, then add an edge between the corresponding vertices. For example, let us say this is an element which is part of multiple sets, let us say 3 sets. So you draw edges between this element and those sets which are containing this element, and so on. Okay. So it may happen that uh, so a set can contain multiple elements, so therefore there could, so the graph would capture essentially this containment relationship between the sets and the elements. Okay, so now you have to show that an ES instance of set cover would mean that there is an ES instance of the dominating set and the other way around. So that part I will leave it to you to think about it, and then we'll move to the next question. But it is possible to do it in a parameterized fashion. So the parameter preserving way, we can do this reduction so that we can say that this is true, and therefore this is definitely not true. Again, since there is a parameterized reduction, so this is also not true. Again, there's a question on reduction. So which of the following statements are true, is or are true? So assume that cliques does not have an FPT algorithm. Okay. So cliques are complicated enough. I mean, so finding the largest clique in a graph, it is complicated enough that it doesn't have an FPT algorithm, that we can assume. So with this assumption, let us look at the first statement. There does not exist a parameterized reduction from vertex cover to independent set. So what is the vertex cover question? We have already seen the definition of vertex cover, and independent set is also we have seen multiple times in this course. So is there a parameterized reduction from vertex cover to independent set? If it is the case, then we will call it false and this is true. And if not, then we'll have to see accordingly. So the first step towards this reduction is to construct an equivalent instance of independent set from the vertex cover instance in what is called the FPT time. And the second step is to prove that if there is a vertex cover of size k or less in the vertex cover instance, then there is an independent set of size k or less in the constructed instance of independent system. Okay. The other way around also you have to prove. So I'll let you think about it for a minute. So we have seen two constructions already.
So in a graph, like if we have a vertex cover of size k, that implies that there is an independent set of size n minus k.
Yes. Yes.
Or maybe it's only true for maximal, minimal vertex cover and maximal independent set.
No, no.
I think it is true for any.
So this is a graph.
Hmm.
So some of the vertices, if they form a vertex cover, then all the
Vertices will be incident to them.
yes, all the edges are incident on them. So all the vertices that are not in vertex cover, they
Will
would,
dependency.
yeah, they cannot have edges among them. So these vertices which are outside of the vertex cover
Hmm.
must induce an independent set. That is true. Yes. So, so what do we mean by a parameterized reduction from vertex cover to independent set? So the parameter for vertex cover is k, but the parameter for the independent set is becoming n minus k. We don't want that to happen. So we have seen fixed parameter tractable algorithms for deciding whether G has a vertex cover of size k or not. Okay, so if G has a, so we can run that algorithm and we can decide, we can find if first is, so you are given an instance of vertex cover. So you run the FPT algorithm on this instance and you will know whether this is an ES instance or no. So if it is an ES instance, then you can find k or less vertices forming a vertex cover in FPT time. That is the first step. And that means the remaining at least n minus k vertices form an independent set. All right. So now what we can do, so how we shall construct this graph H such that it has a set of k isolated vertices. So can we, okay, so K is part of the input. GKN is not within our control. So the now if K is n by 2, then we can say that the existence of an n by 2 vertex cover implies the existence of an n by 2 independent set. So if G comma n by 2 is an yes instance, then G comma n by 2 is an yes instance for the independent set also. And if G comma K is a no instance for the vertex cover, then yeah, I think this requires some more thought. So I'll update about this, that how to go about this parameterized reductions while preserving the parameter. I'm not able to recollect it right now. But this is true that the vertex cover can be reduced independent set in FPT time. So I am not able to recollect the argument. But on the other hand, we have seen in the lectures that the independent set on regular graphs can be reduced from the problem of clique on regular graphs. So since we know that clique does not have an FPT algorithm, so therefore it is unlikely that independent set has an FPT algorithm. So there does not exist a reduction from independent set to vertex cover. So vertex cover is FPT, but independent set is unlikely to have an FPT algorithm. So vertex cover is not as hard as independent set. Okay, so if you have any doubts, you can ask me. It's already 8 o'clock. Okay, so then thank you for joining, and we'll see you in the extra class, most likely on 19th. Uh, Good night.